Welcome to this coding walkthrough. In this session, we'll dive into LeetCode problem number 1446, consecutive characters. This problem challenges us to find the maximum length of a substring with identical consecutive characters. Perfect for sharpening your string manipulation skills, this problem can be solved efficiently with a simple linear traversal. Let's get started. In this problem, you are given a string S that consists of only lowercase English letters. A substring is simply a sequence of characters that are contiguous in the string. Now, the key term here is the power of the string. This is defined as the maximum length of a substring where all the characters are identical, meaning there's only one unique character in that substring. Your task is to calculate and return this power of the string. The input for the problem is a single string S, with its length ranging from 1 to 100,000 characters. The output will be a single integer, representing the maximum length of any substring that fits the given condition. Let's look at an example to make this clearer. Consider the input string S equals LeetCode. The task is to find the longest substring where all the characters are the same. In this case, the substring E is the longest, with a length of 2, as it contains only the character E. So, the output is 2. Similarly, for the string S equals apt_d_dikpa, the longest substring of identical characters is E, which has a length of 5. Therefore, the output is 5. These examples help illustrate the process of identifying and measuring the longest substring with a single unique character. Another example is the string S equals triple-paloo. Here, the longest substring with identical characters is O, which has a length of 5. So, the output is 5. Now take the string S equals horaaaoe. In this case, the substring a stands out, as it has a length of 11. This makes the output for this example 11. These cases demonstrate how the solution identifies and counts consecutive characters efficiently. For the string S equals tourist, the situation is different. Each character in the string appears only once and doesn't repeat consecutively. This means that no substring is longer than one character with only one unique value. Therefore, the output here is 1. These examples cover a range of scenarios, from strings with repeated blocks of characters to those with entirely unique characters. When thinking about edge cases, consider scenarios like the smallest input size. For example, if S has only one character, such as S equals A, the output will obviously be 1, since the entire string is the substring. If all characters in S are unique, such as S equals ABCD, the output will also be 1, as no substring has more than one repeated character. On the other hand, if all characters are the same, like S equals AAAA, the output will be the length of the string, which is 5 in this case. For strings with alternating patterns, like S equals abababab, the output would remain 1, as no block of characters repeats consecutively. These edge cases highlight the importance of considering different types of input when solving the problem. To solve problem number 1446, the goal is to determine the maximum length of a substring where all characters are the same. This can be approached in different ways, each with its own trade-offs. The first approach is the brute force method, where we check all possible substrings in the string. For each substring, we verify if all the characters are identical, and then update the maximum length if needed. To implement this, we use two nested loops. The outer loop marks the start of the substring, and the inner loop examines the consecutive characters. However, this is computationally expensive. The number of substrings in a string of length n is n squared, and verifying each substring takes up to k time, where k is the length of the substring. This results in an overall time complexity of n cubed, in the worst case. While this approach is conceptually straightforward, it's not practical for large strings, especially given the constraints of the problem, where n can go up to 100,000. A more efficient approach is the sliding window method. Here, instead of examining all substrings explicitly, we iterate through the string in one pass, counting the length of consecutive identical characters. When the sequence ends, we update the maximum length and reset the count. This drastically reduces the computational overhead. The sliding window approach has a significant advantage in terms of efficiency. Its time complexity is n, as we process each character of the string exactly once. Additionally, it has a space complexity of 1, since we only use a few variables to track the current run length and the maximum length. This makes it highly scalable for large inputs. Importantly, this approach has no major drawbacks, it's both simple and effective. Another alternative we considered is the two-pointers method, which is conceptually similar to the sliding window approach. Here, we use two pointers to explicitly track the start and end of a sequence of identical characters. When the sequence breaks, we calculate its length, compare it to the maximum length, and then move the start pointer to the next sequence. While this also achieves an O(n) time complexity and O(1) space complexity, the two pointers method can be slightly more verbose in terms of implementation. Ultimately, we selected the sliding window approach as the preferred strategy. It strikes a perfect balance between simplicity and efficiency, and it avoids the need to explicitly manage two pointers. The key insight driving this choice is that we don't need to generate or verify substrings explicitly, tracking consecutive identical characters in a single pass is sufficient. The main insight for solving this problem is that it revolves around finding runs of consecutive identical characters. Instead of constructing substrings, we can focus solely on tracking the length of these runs. This observation plays directly into the sliding window approach, which naturally handles the task by counting consecutive characters and updating the maximum length when the sequence ends. This makes the solution both intuitive and efficient. When comparing the three approaches, brute force is the simplest to understand but suffers from impractical O(n)³ complexity for large inputs. The two-pointers method offers comparable efficiency to the sliding window approach but introduces slightly more implementation complexity. The sliding window approach, on the other hand, stands out as the optimal choice. It is clear, concise, and efficient, with a time complexity of O(n) and a space complexity of O(1). By leveraging the sliding window strategy, we ensure that the solution not only meets the problem's constraints but also remains elegant and easy to implement, making it ideal for competitive programming scenarios. To solve the problem of finding the maximum length of consecutive identical characters in a string, we take a systematic approach using a sliding window or single-pass iteration. The idea is to traverse the string once while maintaining two key variables, one for the maximum streak of identical characters encountered so far, called max_count, and another for the current streak length, called current_count. Initially, max_count is set to 0 because no streak has been observed yet, and current_count is set to 1 since every character, at a minimum, forms a streak of length 1. As we iterate through the string starting from the second character, we compare each character with the one before it. This setup allows us to build our streaks dynamically and efficiently as we move through the string. Now, let's break down how the algorithm handles consecutive characters. If the current character matches the previous one, we simply increment the current_count to extend the streak. However, if the current character is different, it means the streak has ended. At this point, we compare current_count with max_count and update max_count to ensure it always holds the longest streak observed so far. Then, we reset current_count to 1, as we are beginning a new streak with the current character. At the end of the loop, there is a possibility that the longest streak stretches to the very end of the string. To handle this, we perform one final update to max_count, ensuring the result includes the final streak, if applicable. Finally, we return max_count as the result, which represents the length of the longest streak of consecutive identical characters in the string. This approach is highly efficient due to its single-pass nature. By iterating through the string just once and comparing adjacent characters, we avoid the overhead of nested loops that a brute force solution might use. This reduces the time complexity to O(n), where n is the length of the string. Additionally, the algorithm is memory efficient, as it uses only two variables, current_count and max_count, to track the streaks. This keeps the space complexity constant at O(1). It's also important to consider edge cases. For example, if the string is empty, the result is 0 since there are no characters. If the string has only one character, the result is 1 because that single character forms a streak of length 1. In cases where no characters are repeated, the max_count will also be 1. Conversely, if all characters in the string are identical, the max_count will equal the length of the string. This simplicity of design ensures the algorithm handles all scenarios robustly without requiring additional data structures. To better understand the algorithm, let's walk through an example. Consider the input string s equals abecubed. We initialize max_count to 0 and current_count to 1. Starting from the second character, we compare each character with the one before it. The first two comparisons involve a, which are the same, so current_count increments to 3. When we encounter b, it's different from a, so we update max_count to 3 and reset current_count to 1. The next comparison involves two b characters, so current_count increases to 2 before encountering c, which resets the streak again. This process continues as we handle the d characters, where the streak extends to 4. Finally, the character ends the streak, prompting one last update to ensure max_count captures the longest streak. In this example, the longest streak is 4, corresponding to the d characters, and the function returns this as the result. Analyzing the algorithm, we find that it operates with a time complexity of O(n), as we traverse the string just once. The space complexity is O(1), given that only 2 variables are used to track the streaks. This efficiency makes the solution scalable for large strings. The corresponding code implementation is straightforward. We start by initializing max_count and current_count, then iterate through the string while updating these variables based on character comparisons. At the end, one final update ensures the longest streak is accounted for before returning the result. This implementation captures the algorithm's simplicity and efficiency, providing a robust solution to the problem of finding the maximum length of consecutive identical characters in a string. The provided Python implementation solves the problem of finding the maximum power of consecutive characters in a string. The function, maxPower, takes a string s as input and returns the maximum length of a substring where all characters are identical. First, two variables, max_power and current_power, are initialized to 1. These are used to track the maximum streak of consecutive characters and the current streak, respectively. The function then iterates through the string starting from the second character, index 1. For each character, it checks whether it is the same as the previous character. If they are the same, the current_power is increment, and the max_power is updated to the maximum of its current value and current_power. If the characters differ, the current_power is reset to 1, indicating the start of a new streak. After the loop completes, the function returns the value of max_power, which contains the length of the longest substring of consecutive identical characters. This approach efficiently solves the problem in O(n) time, where n is the length of the string, as it requires only a single pass through the string. It also uses O(1) additional space, making it optimal in terms of both time and space complexity. Edge cases, such as strings of length 1, or strings with no repeated characters, are handled naturally by the algorithm. This is the Java implementation of the LeetCode problem number 1446, consecutive characters. The logic mirrors the provided Python solution, where we iterate through the string to calculate the maximum streak of consecutive identical characters. Key differences include the use of Java's char at 4-character access and math.max for updating the maximum streak. The implementation is concise and adheres to Java conventions, such as explicit type declarations. To solve this problem, we start with an example where the input string is LeetCode. First, we initialize two variables, max_power, which keeps track of the highest streak of consecutive characters we've encountered so far, and current_power, which tracks the streak of the current character. Both are set to 1 initially since any non-empty string will have at least one character. Now, as we iterate through the string, we compare each character with the previous one. At index 1, the character is E, which is different from the character at index 0, L. Since the characters are not the same, we reset current_power to 1. The max_power remains 1 because no streak longer than 1 has been seen yet. At index 2, we find another E, which matches the character at index 1. This means we have a streak of 2 consecutive E's, so we increment current_power to 2 and update max_power to the maximum of its current value and current_power, which becomes 2. At index 3, the character is T, which is different from E, so the streak ends, and current_power is reset to 1. the max_power remains 2. Continuing this process for the rest of the string, we find that no streak exceeds 2. Therefore, the longest streak of consecutive characters in LeetCode is 2. With the iteration complete, the final value of max_power is returned, which in this case is 2. This represents the longest streak of consecutive characters in the string LeetCode. Now, let's look at another example where the input string is apt_ddikba. As before, we initialize max_power and current_power to 1 to begin tracking the streaks of consecutive characters. Starting the iteration, at index 1, the character b differs from the character at index 0, so current_power is reset to 1, and max_power stays 1. At index 2, the character is again b, which matches the character at index 1. This gives us a streak of 2 b's, so current_power is incremented to 2, and max_power is updated to 2. At index 3, the character c is different from b, resetting current_power to 1. The max_power remains 2. As we continue iterating, we find a streak of 3 c's, which updates max_power to 3. Then, a streak of 4 d's increases max_power to 4, and finally, a streak of 5 e's updates max_power to 5. After completing the rest of the string, no streak longer than 5 is found. Thus, the longest streak of consecutive characters in apt_ddikba is 5, and we return this value as the result. Now let's consider a third example where the input string is aabap. Again, we start by initializing max_power and current_power to 1. As we iterate through the string, we observe that the characters at indices 1, 2, and 3 are all a, forming a streak of 4 consecutive a's. This increments current_power to 4 and updates max_power to 4. At index 4, the character changes to b, breaking the streak, so current_power is reset to 1, while max_power remains 4. Then, at indices 5, 6, and 7, we see a streak of 4 b's, which matches the current max_power but does not exceed it. Finally, at indices 8 and 9, we find a streak of 2 c's, which is shorter than the current max_power. Thus, the longest streak in this string is 4. After completing the iteration for this example, the final value of max_power is determined to be 4, representing the longest streak of consecutive characters in the string aabap. This value is returned as the output. By following this approach of iterating through the string and comparing adjacent characters, we can efficiently calculate the longest streak of consecutive characters for any given input. The time complexity of the given solution is O(n), where n is the length of the input string. This is because the algorithm performs a single pass through the string using a for loop that iterates from index 1 to n1, resulting in n1 iterations. During each iteration, the operations include comparing the current character with the previous one, which takes constant time, and updating variables like current_power and max_power, which are also constant time operations. When we multiply the number of iterations by the constant work done in each, the total time complexity is O(n). Whether we look at the best case, where all characters are unique, or the worst case, where all characters are the same, the algorithm still performs a single linear traversal of the string. This ensures that the time complexity remains O(n) across all scenarios, including the average case where the string contains a mix of repeating and unique characters. The space complexity of this solution is O(1), meaning it uses constant space regardless of the size of the input string. This is because the algorithm relies on only 2 integer variables, max_power and current_power, to track the maximum streak and the current streak of consecutive characters. These variables require a fixed amount of memory, and no additional data structures like arrays or hash maps are used. Furthermore, the input string is read but not modified, so no extra space is allocated for it. Since the memory requirements do not grow with the input size, the total space consumption is constant, making the space complexity O(1). When comparing this optimized solution to a brute force approach, the advantages become clear. A naive solution might involve iterating through all possible substrings of the input string, checking for consecutive characters in each substring, and calculating the streak lengths. This would require nested loops, one to define the starting points of substrings and another to compute streak lengths for each. Such an approach would have a time complexity of O(n²), as the number of iterations grows quadratically with the input size. Additionally, it might require extra space to store substrings. In contrast, the current solution avoids nested iterations by maintaining a running streak count during a single pass through the string, resulting in O(n) time complexity. It also eliminates the need for extra space, achieving O(1) space complexity. This optimized approach is mathematically validated, as the loop iterates n1 times with each iteration taking constant time, leading to O(n) time complexity. The memory usage is dominated by the two integer variables, confirming the O(1) space complexity. This makes the current solution both time and space efficient, demonstrating its optimality for this problem. When solving this problem, there are a few common mistakes to watch out for. First, not handling edge cases properly can lead to serious issues. For example, if the input string is empty or contains only one character, your code might crash or produce incorrect results. To avoid this, make sure to explicitly check for these situations and return the appropriate value, such as 0 for an empty string or 1 for a single character. Another mistake is relying on inefficient nested loops to generate all substrings and check their validity. This brute force approach can quickly become computationally expensive, with a complexity of O(n) squared or worse. Instead, you should aim for a more efficient linear solution by using a single traversal and a counter to track consecutive characters. Lastly, it's important to correctly update the maximum length. If you only update it after the loop ends, you might miss the longest streak if it happens at the very end of the string. To prevent this, ensure you update the maximum length after processing each character in the string. Another mistake to be mindful of is not resetting the counter correctly when a new character is encountered. If the counter isn't reset to 1 at the start of a new streak, it might accumulate values incorrectly, leading to wrong results. Always remember to reset the counter as soon as you detect a change in characters. Additionally, off-by-one errors in indexing can be a frequent trap. For instance, when comparing characters like S(i) and S(i1), it's easy to accidentally access an index outside the bounds of the string, especially for smaller inputs. This can cause runtime errors or invalid comparisons. To handle this, carefully design your loop to ensure indices are always within valid ranges, and consider starting from the second character if needed to avoid accessing S(1). Attention to these details can make your solution both robust and reliable. Now, let's discuss some key insights for interviews. This problem is essentially about recognizing the pattern of consecutive elements, which is a variation of the sliding window or two-pointer approach. While a single pointer is sufficient here, understanding these patterns can help you identify similar problems. Interviewers might also challenge you to optimize your solution. For example, transitioning from an O(n) squared brute force approach to an O(n) linear traversal shows a strong understanding of efficiency. Furthermore, demonstrating edge case awareness is critical. Always bring up scenarios like empty strings, single character strings, or strings where all characters are the same. Finally, you should prepare for follow-up questions that explore variations of the problem. For instance, you might be asked to return the substring itself instead of just the length, or to handle cases with multiple longest substrings. These questions test your ability to adapt and think critically. Related problems like max consecutive ones or longest substring without repeating characters are good practice for mastering these concepts. Finally, let's explore a few alternative approaches to solving this problem. One option is a linear scan using two pointers. This method involves maintaining two pointers to track the start and end of a streak and updating the maximum length whenever the streak ends. While this method avoids manually resetting counters, its implementation can be slightly more complex. Another approach is to pre-process the string by grouping consecutive characters along with their counts. Once you have these groups, you can easily find the maximum count. While this method improves readability, it requires extra space to store the groups. Lastly, you could use a recursive approach, dividing the string into smaller sections and computing the longest streak in each half, then merging the results. However, recursion introduces additional overhead and is typically less efficient than iterative solutions. Each of these alternatives has its own trade-offs, so it's important to choose the best fit based on the problem requirements and constraints. Great job making it to the end. In summary, we tackled LeetCode problem number 1446, exploring an efficient method to find the longest streak of consecutive characters. This problem underscores the importance of mastering string traversal and optimization techniques. Thanks for watching, and I hope you'll join us for more problem-solving sessions in the future. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!